Namaskar. In today's lecture, which is second in the series, Fundamentals of Physics, a video lecture series by me, I will be talking about kinematics in one dimension, and I am making presentation of part first for the purpose. In this part first lecture of kinematics in one dimension, I will be pointing out what essential mathematics you must know to understand the subject of kinematics in one dimension. I begin my lecture with a quotation from Sir Richard P. Feynman, and he said, "Don't get frightened by not knowing things. I have approximate answers and possible beliefs and different degrees of certainty about different things, but I am not absolutely sure of anything. There are many things I don't know anything about. It doesn't frighten me." Richard P. Feynman. So we believe that we may not be knowing how to deal with the problem of kinematics of a particle in one dimension, but it's a beginning, and in due course of time we would be knowing about it. There is nothing to worry about in this manner. So we start our journey of understanding the fundamentals of physics through this first topic, kinematics of particle in one dimension. So let's begin. And before the taking up the topic, I would point out that in previous lecture we have discussed certain aspects and pointing that science as systematic study of nature. We have also discussed what we mean by nature, set of natural systems, and the study of science involves both scientific theory and scientific experiment. Physics is the fundamental science, and theoretical framework is essential for understanding even experiments in physics, and we will be developing and changing theoretical framework because we can discard a theoretical framework if it doesn't agree with experiments in science. In physics, we consider physical systems, and physical systems possess physical characteristics. Some of the characteristics can be specified in qualitative manner only, but most of the characteristics of our interest are the characteristics which can be measured in experiments and which can be specified in quantitative manners and which we call physical quantities. This particular initial part of the series would be pertaining to classical physics, and classical physics framework was also explained in the very first talk of the series, introducing and giving a prelude to the series. Now let us choose the simplest system for beginning our study, and the simplest system is a hypothetical system called particle, which I will name Newtonian particle. A Newtonian particle is conceptualized in Newtonian mechanics in a typical way. A Newtonian particle is one which has point size, which is structureless or indivisible, and which possesses physical characteristics. And as you know, point size objects cannot be realized in experiments, and therefore this particular system is a hypothetical system. And since it is structureless, cannot be considered in terms of the subsystem, since there are no part involved. But this particular hypothetical system can be a subsystem of some another system. And for example, later we will come to know and discuss that the dynamics of a body can be described in terms of the dynamics of a particle, and because a body consists of particles. At the same time, a physical system must possess physical characteristics. If it is not having any physical characteristics, it is of no importance, in physics, and therefore in this particular study the particle chosen will have at least one property which we want to have it, and that is called mass, which is an intrinsic property, which is because of its existence. Mass, actually later we will learn, is the measure of a fundamental property, and that property is called inertia, and mass is a measure of inertia in rectilinear motion, and it's an intrinsic property. But to develop the theoretical framework, we will have to define a set of extrinsic properties, because in terms of those extrinsic properties and in terms of that analysis, we will be able to understand the behavior of the system, and which primarily means the change in the state of the system, which here in case of particle, a change in the location of the particle with time will be called change in the state of particle, or will be referred as motion of particle. For specifying the state in terms of its location of the particle at an instant, because at different instant it may be at different location, we need to know and learn certain essential mathematics. Primarily objective of this lecture, as I told you earlier, is to point out that what mathematics you must be knowing to move further in this course. And as you have gone through earlier courses in school, so most of the things which I would have been pointing out in the lecture you have already studied in schools, and it is just time that the knowledge which you have acquired in schools for about this mathematics will be very, very useful in our understanding. So we have to introduce one-dimensional space and one-dimensional time in order to describe the motion, and that motion at this particular moment we restrict ourselves to the rectilinear motion and kinematical description of the rectilinear motion. Later on I will introduce the dynamics, where the cause of the motion would also be understood in terms of Newtonian mechanics framework. So later on we will develop dynamics, but right now we limit ourselves to the kinematics of rectilinear motion of a particle. Now, as pointed out earlier, that in classical physics the natural system will be mapped on a formal system, encoded to a formal system, and the theoretical framework will be used to manipulate the normal system and understand the behavior, and then it will be decoded, and the implications which we could discover through this method can be verified in experiments. So the question which we will take as an example here is the free fall of any object from height h. So object falls from height h to the ground. That will be chosen as the first example for describing rectilinear motion kinematics. So why I am choosing hypothetical particle, that is also a relevant question, and one should understand it. And the point number one is that it involves simple mathematics in understanding. So for beginning it's very good. Number two is that the behavior of real system, though it is hypothetical, can be understood in terms of it. And for example, later it will become clear that translational motion of a rigid body is equivalent to that of particle of same mass but located at the center of mass. But the concept of rigid body and concept of center of mass will be introduced later in this lecture. So wait for that. Framework which we are developing right now will be further extended to understand real natural system and to understand other kinds of motions like rotational motion and the combination of rotational and translation motion, in particular rolling motion, etc. So we have kinematics of a particle in one dimension as an objective, and we choose the example of free fall from height h of an object which has a structure. Since object may be an apple, object may be anything, but the object is not a particle, is not a point-side object, and therefore it is having a structure. But we are assuming that we can assume it and encode it by treating it as a particle on a particular point in this one-dimensional space which will be introduced here. But remember, start from the beginning. I would make it clear that if this falling apple get exploded during the fall, then the dynamics or kinematics which we will be learning here will not be of any use. And it's important because we have assumed that system is indivisible. But in explosion, the fact that system is made of, or the object is made of, particles and will be manifesting with the change in the structure. So it cannot be considered structureless because structure will be changing in course of explosion, and therefore the mathematical analysis which we will learn initially will not be applicable to such a case. Similarly, some natural phenomenon will happen definitely when the object falls on the ground and hit the ground, the collision occurs, and right now we are not interested in that phenomenon of collision. We are only interested in the phenomenon of free fall, which is that starts from the moment when the apple or the object is released from height h and which terminates when the apple or the object touches the ground. Now I shall be pointing out what mathematics you must know and why it is important to know that particular mathematics in this context. You know that most of the objects which you see in daily life are three-dimensional objects, which means they have three spatial dimensions and therefore they have some specific volume and specific value of surface areas. In picture, several such objects have been shown, but every object is having some specific volume and some specific area. So these are three-dimensional objects which we can see. Number of dimension may be more than 3 in hypothetical description, but in as far as our perception or vision is concerned, we have a three-dimensional vision and we can see 3 dimensions. So 3-dimensional objects we find in our surroundings. But there are certain objects which can be considered as 2-dimensional objects because one of the dimension is very very small or of negligible value and therefore can be ignored. And so these objects which I call 3-dimensional will be having, say, that particular dimension called thickness as very very small, and therefore these objects are referred as 2-dimensional objects. Pictures of several such 2-dimensional objects are shown in this slide. Now I come to the next, the 1-dimensional objects. If the 2 dimensions are negligible and can be ignored, like in case of a wire, what we have that we can ignore the cross section of the wire. If the cross section is very very small, and very very small makes no meaning, if it is very very small in comparison to what we call length of the wire, then we can say that length of the wire and the dimensions involved in defining cross section will be compared. You can't compare length with the area, but when I say for example it has circular cross section, then if its length is large and much larger in comparison to the radius of the cross section, then we can ignore the cross section or the 2 dimensions, and the object which we are having will behave like a 1-dimensional object. And so natural system of 1-dimensional object can be a straight metal wire, and as pointed out earlier, in classical physics we have to map it or encode it to a formal system, and then we have to introduce certain quantities. So now we will come to that. So let's begin the study of the simplest system called particle and try to get some picture of mathematics which is required for understanding its motion in one-dimensional space and one-dimensional time, and the motion which I have earlier referred as a rectangular motion. To understand what mathematics you should know, I will point out now. And the first is the Euclidean geometry. You may have heard of Euclid, and Euclid was in era before Common Era, and he has contributed and is known as father of geometry or founder of geometry, a very important branch of mathematics, and I am sure you have already learned it in school. The Euclid was contemporary of Ptolemy and first in Europe and Chanakya in India, you can say. And Aryabhatta came much later than the Chanakya. So to understand the physics, we must also understand the chronological order in which our understanding has improved. So Euclid has written and his work, which is known as which has been published later on by some authors based on the scripts available, and that book is named Elements. And in Elements, he has described the Euclidean geometry in an axiomatic system, and that's very important. Axiomatic system or axiomatic mathematics, and the Euclidean geometry is one of the best example for describing axiomatic system or axiomatic mathematics. An axiomatic system should begin with a list of the terms and notions and that it will use. The definitions are given, and the definition says that one term that will be used in case of Euclidean geometry, it is a point, and the next few definitions give some more terms and notions which will be used in Euclidean geometry, and we have to understand that. And the description of a point as given by Euclid in the book Elements is that which has no part. And since my chosen physical system particle is also not having any part, so you can definitely realize that this would be very useful. The point, the concept of point in Euclidean geometry would be very useful for me in developing a theoretical framework for kinematics of the particle. So the Euclid will be treating a point as having no dimensions, which means no width, no length or no breadth. So and located and indivisible at some indivisible. That's true. Here I have reproduced, and for learning this topic you can go through, if you are in India, the NCERT book at 9th level for the 9th level course on mathematics, and that provides good information and literature on Euclid geometry. Remember, in this lecture I am pointing out the essential mathematics which you must know, but I will not describe mathematical structure of the theory in detail because I wish to focus only on conceptual structures and fundamentals of physics. So Euclid have given many definitions, and the first definition is that a point is that which has no part. Second definition is a line is breadthless length. The third definition is the ends of a line are points. Fourth is that a straight line is a line which lies evenly with the point on itself. All the definitions and the entire literature is available, and it was published, and a very good source of element is this book which was published in English in 1570. And therefore you can also realize that Galileo, which was alive in the period 1564 to 1642, and Sir Isaac Newton, another great scientist whose contribution will come up in the era 1643 to 1727. So in that period the literature was known. But since Euclid was born before Common Era, 365 before Common Era, so you can just understand roughly that 2000 years have gap is between Isaac Newton and the Euclid. And the manuscript could survive and we could understand and develop the science. So the names which you know who have contributed significantly in physics are limited, but actually the people involved in development of those ideas, the list will be very, very long. So mathematics is different. It's a formal science definitely, but it is a human construct. It is a man-made thing. It's not a natural system like which we discuss in physics. It doesn't exist in nature. Mathematics is a human construct and it has been constructed by us, and so it's our mental construct. Mathematics can be constructed, and in different ways of constructing mathematics are there, but the way which Euclid has pointed out involves definitions. As I have said earlier, few definitions I have pointed out, then stating the obvious universal truth either as postulates or axioms, and the third is that using that structure, mathematical structure, then trying to prove certain theorems or logically deriving theorems out of it, and then these theorems can further lead to lemmas and corollaries. If you have learned Euclidean geometry or any branch of geometry, any branch of mathematics which has been developed in axiomatic manner, you may have noticed this feature. So, meaning of the notion like particle, which is defined in Euclidean geometry, it comes from properties about or properties of particle which are assumed later in axioms or through the postulates. But what kind of mathematics a physicist or scientist should consider? Only that mathematics which is consistent and which is not self-contradictory. So there should not be any contradiction, and consistency in mathematics is an essential feature for us, for scientists. Mathematics is very, very essential and useful in theoretical analysis in natural sciences, and more so in case of physics. So we need to have a formal system to encode our particle. In mathematics, an axiomatic system is any set of axioms from which some or all axioms can be used in conjunction to logically derived theorems. So a theory like mathematics should be consistent, relatively self-contained body of knowledge which usually contains an axiomatic system and all its derived theorem. An axiomatic system that is completely described in a special kind of formal system. Definitely, geometry is a formal system, but not suitable for directly describing the chosen hypothetical system called particle. So we have to learn other mathematics also, other branches of mathematics also. One is about number systems. Everyone is familiar with number system, and so I need not say much about it. But you may not be knowing that the kind of the numbers which we know today, in fact, the knowledge about number system, the history of that is before Common Era, 4000 years before Common Era, the Sumerians were knowing things, and they had not one or two but 12 separate counting systems, and one of the counting system was base 60 sexagesimal counting system. A picture is shown in this slide. Now you have learned in your school courses of mathematics about the system which we call decimal digital number systems. You may also be knowing about binary digital number systems which are very useful in binary digital computers. But at least everybody knows about decimal number system. Decimal numeral system has number of 10 as its base. Instead of 60, number 10 as its base, and the term decimal is used in many different with many different meaning in this context. The term decimal is also used for a number written in this system or a fraction expressed in this system by using this system, and which involves so-called decimal point. But a number written in decimal notation involves the use of one or more of 10 distinct symbols or fundamental units called digits. These digits, these numbers 1, 2, 3, 4, 5, 6, 7, 8, 9 and 0, these are mathematical notions. These are not real objects or real natural system. The digits are often used with a decimal separator which indicates the start of a fractional part. And since you are familiar with it, please revise if you have forgotten certain things. Otherwise, the previous knowledge would be very much helpful for us. The decimal system is also a positional number system. It has positions for units, for tens, hundreds, and similarly on the other side of the decimal point, maybe a 1/10th or 1/100th and so on. But the positional number system works in such a manner that each position has a value 10 times that of the position to its right. And so apprise yourself about the digital number systems. Then there are several number systems which you may have learned in your courses, and those should be revised for understanding physics. In mathematics, the natural numbers are those which are used for counting. Give an example, there were 5 Pandavas in Mahabharata, and also for ordering. The example given here in the slide is that India is 6th largest economy of the world, and in common mathematical terminology, the words used for counting or numbers used for countings are called cardinal numbers, and the numbers which are used for ordering are ordinal numbers. But all numbers are not ordinal numbers. We will come to, and I will explain whenever such a thing or concept would become essential in understanding physics. But you have learned about all these number systems: natural number and set of the natural number denoted by the and then the concept of zero, which is very very important. And if zero we do not have, then we cannot develop consistent mathematics, and zero is essential for development of consistent mathematics of number systems. And concept of whole number, which means that natural number plus zero. And then we have the concept which we call negative numbers, and negative numbers you understand that corresponding to 5 we have a negative number which is -5, which is also called additive inverse of the number 5, because if you add that to the 5 then the sum will be 0. So we have concept of negative numbers. Then if we include negative numbers plus whole numbers, then we have a set which we call set of integers. These are numbers, but their mathematics is not very very useful in understanding the problem which I have on mind, and therefore I will have to move further. And you have learned about a rational number. A rational number is one which can be expressed as the ratio of two integers. For example, 3/7 or 22/7. So you can express a number in terms of the ratio of two integers, but there is a condition that the denominator should not be equal to 0, and that you must have learned, and your mathematics teacher must have explained to you that why it cannot be. And then there are numbers which are what we call real numbers, but which are not rational numbers, and they are named as irrational number. So the set of all real number is of importance to us, and it contains rational number as well as it contains irrational numbers. Rational numbers forms a rational numbers form a countable set, and irrational numbers and the total real numbers forms an uncountable set. All these terms you may have learned earlier, so I skip discussion on it. And you may be knowing that we will also have to move from real numbers and introduce new kinds of numbers, complex numbers, to understand the physics. But I will speak about it whenever a necessity will arise. The necessity at the present time is that if you want to understand this particular course, kinematics in one dimension, then you need to understand the mathematics of real number in addition to what I have told you earlier, the Euclidean geometry. But Third branch, which will be essential for our understanding, is called algebra. And algebra is different than arithmetic. In arithmetic, we use numbers and operations which can be performed on numbers. But in algebra, the arithmetic is similar to arithmetic in the sense that the numbers are replaced by the letters, and these letters can have any value from a given set, and that's the kind of development which has taken place long back, but in 9th century at 20 CE, and Muhammad Busha Khwarizmi has contributed in development of this branch of mathematics, algebra, which you must have learned. So the knowledge of algebra is also essential. It helps us in understanding the subject. Then comes the marriage between algebra and geometry. So initially, algebra and geometry were different subjects, but this great man shown in the picture above me, René Descartes, he explained that and developed the new approach of geometry, which is now known as coordinate geometry. And the system which he has developed is based on coordinates, and these coordinates are called in his honor as Cartesian coordinates. So in 17th century, he revolutionized the mathematics by establishing a systematic link between geometry and algebra. Before that period, the geometry and algebra were considered very important mathematical topics or subjects, but the real breakthrough is due to René Descartes, because he contributed in establishing what one says a link or establishing a marriage between two different branches of mathematics, and that's algebra and geometry. And the new geometry came, which you have also learned in school, called coordinate geometry. And this coordinate geometry would be very essential and would be mainly used in our description, as you will realize very soon. From that, we can build also a concept of Euclidean space. So because Euclid has defined a point in the space, point he has definition he has given. Now the set of all points, and so set theory you must also know, and I have not mentioned it earlier, but it is an essential branch of mathematics which everybody must understand to understand other branches of mathematics. So point is located in what we call space, and location is described in Cartesian geometry of the point by specifying the coordinates. So different set of coordinates specify the locations of different point. But the space has dimension, and the word dimension would also appear in our discussion, but it has different meaning in different contexts or different references. For example, here in Cartesian geometry, when we say dimension and of space, then it has a particular meaning. But when you say that energy and force have certain dimensions which can be expressed in terms of m, l and t, the things which will be introduced later, that has a different meaning of dimension. One dimensional means one coordinate will be sufficient, and required meaning is to specify the state of the system. Two dimensional, two coordinates. Three dimensional, three coordinates. And since we can only see three dimensional objects, maybe in the beginning of the course the limit will be up to three dimensional only. But as you would move further, you would realize that we can generalize this, and in n dimensional space, n coordinates are required, where n is any natural number. So you can have a 25 or 24 or 10 dimensional space, or even more dimensional time also. But we will come to that whenever it will become important. Now a space is called real space if the coordinates are real number. So I have said real numbers are important because Cartesian geometry is the most important. In Cartesian geometry, the description is in terms of coordinates, and coordinates are real numbers. And if you do not know the properties of the real numbers, the theorems, lemmas and corollaries associated with real numbers, the axioms and postulate associated with the real numbers, then you would find it difficult. But there is no problem. If you face difficulty, then you can consult the literature which is available on this topic. Now, to give a further understanding of what we call one-dimensional Euclidean space or one-dimensional real Euclidean space, it can be one can understand it in terms of what is called real line. And about real line also, you have understood it in school courses. A real line is a line on which the real numbers can be expressed. So every point in the real line will correspond to a real number. But to specify the real numbers on the real line, you have to make a choice of what we call origin, where the number 0 will be assigned or mapped, and then you can have all numbers on real line. That you all understand, so I will not explain it further, but I will point out that the real numbers are ordinal numbers in the sense that given two real numbers A and B, we can make a decision whether A is greater than B or A is less than B or A is equal to B, and that order can be decided. So further, you know that there is an important point or aspect of real number is that between any two real numbers there are infinite rational numbers as well as infinite irrational number. So that's a thing which you already know. Then the distance between points. So when you specify the real numbers on the real line, and suppose a particular number which I am labeling as A is specified at the number A, small a, and a specific label B at a point which has coordinate B. So now most important thing in this real line is to specify distance between the 2 points, and you have learned it in your school course, and you know that distance between 2 points A and B specified by coordinates small a and small b will be specified in terms of A minus B modulus, and modulus of A minus B or the magnitude or norm of A minus B is therefore very, very important. And you also know that modulus of A minus B is always a positive number. So distance is always a positive number. Distance cannot be a negative number. Once you master mathematics of real line, which is a very consistent mathematics, we will make use of it in physics. We can make use of it in physics, and that's important. And these subjects, if you have studied earlier, then in my forthcoming talks I will be making use of knowledge obtained through learning of these subjects. Again, I list those subjects which you should revise or for which you must have references if required for consultation, and that is set theory, Euclidean geometry, number system, algebra, coordinate geometry, one-dimensional Euclidean space. And with this part, the second lecture, I will conclude by quoting again, and these quotes which I have now chosen are about mathematics. René Descartes, the great mathematician and philosopher, has said that, but in my opinion, all things in nature occur mathematically. Somebody has also said that all knowledge is mathematical. You will understand this particular point of view in due course of time. Then I would also like to quote here Werner Heisenberg, one of the founder of quantum mechanics. He has said, I think that modern physics has definitely decided in favor of Plato, the philosopher. In fact, the smallest units of matter are not physical objects in the ordinary sense. They are forms, ideas which can be expressed unambiguously only in mathematical language. And by saying that, Werner Heisenberg has emphasized that mathematical language is very, very important in learning physics. So this essential mathematics which you should recollect I have pointed out. And now in the next talk I will continue the part 2 of kinematics of particle in one dimension, and I will be introducing and defining and specifying how it can be measured and other issues called length. So in the next talk we will discuss length as a physical quantity. Thank you very much for watching this second lecture on YouTube channel A for Science, and please subscribe and also click the bell icon so that you will get notification whenever my third lecture will be uploaded. These lectures are also available in bilingual form, which means Hindi and English, on the same channel. Thank you very much.